Welcome back to After Hours Engineering. At this point, we built several key components, the register, the LU, and our most complex component, the memory. This leaves us with just a few modules to go, and in this episode we're going to knock out three more, the RegisterFile, the PC, and the MUX, which will put us just one step closer to where we need to go. However, this time we're only going to simulate because of the simplicity of these components. So let's start with the register file first. Register files are similar to memory in that their instantiation is identical, yet they have triple address inputs and dual outputs. The two addresses specify source locations and the remaining specify the destination location. The data output is defined as asynchronous via a continuous assignment, which we learned in the previous episode negates any kind of inference of BRAM. Here we have the register file module that supports that diagram. As usual, we have our parameter inputs with default values. We have our clock input, the write enable, the data input, registry destination input, our two source selectors, and the two outputs. Here is our memory bank, and as you can see, it is identical to memory. Yet the rest of the code looks something vaguely similar to memory. For example, you may recognize this section as the dual port write. And in the bottom is the continuous assignment that we saw when we were trying to break the inference. This is the register file definition that we're going to use for this module. Now let's look at the register file test bench for this module. So as usual, we have our timescale set up, some outputs. We have our inputs and outputs to the device under test. Here's the device under test, our register file. Here's our clock that we're going to synchronize. And then we set up some default values before the test actually begin. Here's where our always block sits. And the first thing we're going to do is load register 0 with a specific value. So we set the destination to 0. And we're also going to make our assertion on the output of source 1. So here we are. As usual, all of our modules operate on a positive and negative edge cycle. On the positive edge, we're setting signals up, and on the negative edge, we're taking action. And here we're testing for the assertion that we loaded A. Again, we do the same thing, but this time for register 1 with a different value. We set up the destination as 1. We're going to again do our assertion on this output of source 1. And then finally, we're just going to turn right around and read register 0 and then do assertion on that. That's the test bench. Now we're ready to run the simulation. So let's bring up the terminal and execute the make sim command. And it brings up GTK wave. So this is a reflection of our test bench. And remember, we were loading register 0 with the A0 value here. You can see that the data in has been set. On the positive end of the clock, we're setting up all of our signals. So there the write enable goes low because we are writing. And then on the negative edge is when the action takes place. And here is the output of that register. We know that any register is continuously assigned. It's immediately available on the output as a reflection of the destination source 1 and source 2. And remember, we set source 1 to 0. So then we go to the next positive edge of the clock and we bring the write enable flag high. We go to the negative edge and we keep it high. That was that short little positive negative edge enablement. We know in our test bench on the next rising edge we change the input value to an A, and we change our destination register to a 1 and our source output to a 1 as well. And then we wait to the negative edge of the clock, and sure enough, our output comes out. So it does look like our register is working, at least signal-wise. And again, this is a non-comprehensive test. Formal verification would do a far more extensive test on this, and we're not doing that with this very basic processor. So it looks like our register file is working. Great. We now have a working registry file. It's very similar to memory, but with a few extra data paths. Let's move on to building the program counter, or PC. In the upper right hand corner we have the diagram for the program counter, and in the background we have the module itself. We have our usual input parameters, and we have our inputs and outputs. We have the reset, the clock, the load, the increment, the data in, and the data out. The data out is a register in and of itself. Again, in our processor, all of our components do things on the negative edge. And in this case, if the reset is active low, we load the output register with 0. If the load is low, then we take the data in and set it to the data out. And if the increment is low, we take whatever the value of the data register is and add the word size to it, which in our case will always be 1, because all of our instructions and data all take up a single memory location. And then finally, if none of these are active, the output remains the same. Next, we have the test bench to go along with the program counter, and it has all of the usual suspects in it: our input parameters, output parameters, the device under test, which is the program counter, our clocks to synchronize, and then any initialize statements we have. For a program counter, we're going to test again basic functionality, non-comprehensive test. The first thing we're going to do is reset it, dragging the reset line low, and we don't care what the inputs are. We wait on the negative edge of the clock and we do an assertion on the output, and hopefully it went to 0 because we were trying to reset. Then we turn around and try to load the PC with a specific address or just some arbitrary value. Again, we wait till the negative edge of the clock when the action of the component takes place, and we test for our assertion. We do turn around and make sure that we can reset it back to 0. That's what this does. And then finally we test out the main feature of the program counter, which is the ability to increment itself. So we disable the reset, we disable the load, and we enable counting. So on the negative edge of the clock, the PC counter will bump up by 1, and we test an assertion for that. And we do it again, we make another assertion, do it one more time, and then make another assertion. That's the test bench. Again, non-comprehensive. Now we're ready to run our test bench. So we'll bring up our terminal and we will run the simulator and take a look at its output. Remember, in the test bench and in all of our components, we do setups on the rising edge and take action on the falling edge. So here on the rising edge of the first clock, we are doing a reset. That was the first thing we were doing in our test bench. And sure enough, on the falling edge of the clock, the register is reset. On the rising edge of the next clock, we are loading in the register with A0. So we bring the load flag low. And again, on the negative edge, it loads that value into the register. Excellent. That's as we expected. And then on the next rising edge of the clock, we set up for a increment. And so, or actually in this case, we're just waiting one clock and resetting. And that's what we expect. We reset. On the next clock, we set up for an increment, and that's this signal right here. Again, on the negative edge, it increments on 1. The action took place. Then we do it again, and we do it one more time. And sure enough, it's incrementing 1, 2, and 3. So it looks like the program counter is working. Finally, we build the simplest of components, the multiplexer, or MUX. Let's do it. In the upper right hand corner, we have the diagram for a multiplexer, and in this case it's a 4-input multiplexer. But in the file itself we have several. We have 3 of them: a 2-input, a 4-input, and an 8-input. We'll look at just the 4-input because all of them are identical. We have our selection input, we have our 4 data inputs, and we have the single output. So one of these 4 will be routed to this output. The way to implement a MUX in Verilog, or at least one of the many ways to do it, is to use the ternary operator and then chain them all together one after the other. And again, you'll see that in the MUX 8 and in the MUX 2. They're all chained together. And that's our MUXes. Now let's take a look at the test bench. We have our usual suspects, the inputs and the outputs, our clock, the device under test, which I've arbitrarily chosen to be a MUX 4. We have our clock, some defaults, and then finally we set up the input to our MUX and we default the select indicator to 0. And in this case you can see I'm taking the letter A and I'm moving each A to the left 1 position. This makes it really obvious what's happening in the output. and then I go through and I do assertions on every one of those combinations. That's the test bench. Now we're ready to run this simulation, so let's bring up the terminal and run the simulation. And here is the GTK wave output. And as in the test bench, we set up our select statement to false to 0. We set each one of our inputs to those letter A's as they move along to the left side. In this case, we're not using a clock, we're using the Verilog's delay factor in. And here is the output of the first delay as we switch the select statement to 1, then we select it to 2, and then finally to 3. And we can see that the letter A is going. If I double click this, you'll see that the pattern is moving along the inputs. And there you go, our Mux seems to be working. Excellent, we now have 3 more components, the RegisterFile, the PC, and the Mux, which makes our 4th, 5th, and 6th major component. But let's cherish this a minute, because the next component is the most complex component of the entire build, the control matrix. This module ties it all together into a single cohesive state machine, which shortens the road on our journey towards building a softcore processor, the A09. We're getting really close now. Until next time.